Okay, so we'll call it trig problem solving. I'll zoom in to read it a little. It makes a little more sense to us and a little clearer to read. So the trunk of a leaning tree makes an angle of 12 degrees with the vertical. Oh, okay, that's interesting. To prevent the tree from falling over, a 35-meter rope is attached to the top of the tree and is pegged into level ground some distance away. If the tree is 20 meters from its base to its top, calculate the angle the rope makes with the ground to the nearest degree. Okay, there's a lot of information. First of all, we normally consider trees to be, perpendicular to the ground. But this case is a little different. So we're going to reread that part. This is how I would normally think of a tree. For some reason, I have a big red tree here. This one is leaning. So the trunk of a leaning tree is making an angle of 12 degrees with the vertical. So this is not correct. We have a scenario where, maybe I'll make the tree green here. Okay. It's on a bit of an angle. Okay. And we'll also draw a vertical line here. I'll draw that one in red just so we can see, but it says it's making an angle of 12 degrees with the vertical. So in this case, I could say that's here. Okay, I draw a vertical line there, 12 degrees. Or, I'm going to show you, I could technically draw another vertical right where it's hitting the ground. And if I draw that one, the angle with the vertical would be this one here, both 12 degrees. This technically works, okay? And the reason this works is alternating angles. Here's my tree. I'm trying to color it in so it looks a little more like a tree. These are technically two parallel lines, these verticals. So you have this alternating angle rule. They talk about it in grade 9, I believe it is. But either of those works for us, okay? We're going to make a right angle triangle probably at some point. Okay. The next it says, to prevent the tree from falling over, a 35-meter rope is attached to the top of the tree and is pegged into level ground some distance away. This is interesting, okay? I'm going to superimpose this picture. It's always good to try to make a vertical if we can. I'm going to represent the tree with kind of a black line now. The next part is our rope. I'm going to make the assumption that the rope is going in this direction, okay? It could technically go the other direction, but I feel like physics wouldn't support that. And we're going to talk about that in a second. So remember, this makes a, with the vertical, draw that vertical line here. So this is 12 degrees. That's 12 degrees there. The rope itself is 35 meters long. And then they told us that the tree is 20 meters, okay? So the setup for this is probably part of the hardest part to this, is setting this whole piece up. I'm going to show you, because this is a bit ambiguous. They didn't tell us which way the rope is, but I'm going to try to represent it one other way. And then we'll do some logic. I get the feeling it's not that way. If the rope was going this way, do you think the rope would support the tree?
No.
No, ropes usually create tension. They give you like a pull, right? So for instance, when we peg this rope into the ground over here above, usually there's tension kind of heading that way, right? And that makes sense because the tree's here. It's probably trying to fall in this direction. So we put an opposite force to it, right? To keep it up. Here, the tree is falling in this direction. So if we put tension this way, I imagine that just means the tree is going to continuously fall down. Okay, so we're going to go on some logic and say the rope was not pegged this way. We'll use this example we have here. Calculate the angle the rope makes with the ground to the nearest degree. Okay, so what they really want us to find is this piece here. Call that the theta. What is theta at that point? So we have two lengths. We have the length of the rope, which is 35 meters. And we have the length of the tree, which is 20 meters. We don't have an internal angle. Can we find any internal angles from what you see? I'm going to redraw this triangle just a little bit because I know that vertical kind of throws it off a little. But if we were to redraw it, we roughly have this scenario here. Guess I'm drawing it in green. I didn't mean to, but we essentially have this scenario, 35, 20, okay? And we're looking for this, theta. We need at least 3 pieces of a triangle. Looking up here, we kind of have part of an angle, 12 degrees. But I would need the rest of this. Any idea what the rest of that would be?
Wouldn't it be 180 minus 12?
180 would give us a flat line, and then that would give us this and this, but we don't know how they're split. It's not technically down the middle, but if you remember this red line, this is a vertical. So assuming the ground is level, what angle does a vertical line and a horizontal line make with each other?
90.
Yeah, okay. So then we can make a bit of an assumption here. We're going to erase that. We're going to say that this is actually a 90-degree angle. And as soon as we do that, we now know that this is 90 degrees. So what would this angle then be if that's 90 degrees?
That would be... Oh, I'm not sure.
Okay, we're going to take the 90 and we're going to take this 12 degree and we're just going to add them together. We add them together, that'll actually give us the entire obtuse angle, right? Because this one's kind of passing the 90 degree, and that would be the same as this one here. So in this case, 90 and 12 ends up being 102. So we know this internal angle is 102. From that information, we can make a decision. What do we want to use? So we can bring up a whole bunch of tools. There's a primary trig ratios. So you have your SOHCAHTOA. You have Sine Law. There's an E there. Cosine Law. Technically, there's a tangent law, but we don't go through it. It's not important. You can solve everything with these ones. Do you know what what's the rule for using the primary trig ratios? Do you know what type of triangle you have to have?
90.
Yeah.
90 degrees.
And if we take a look here, nothing here proves that this is a 90-degree triangle, so our primary trig ratios are probably out of the question. Cosine law and sine law. So for sine law, you need opposite angle and an opposite side. You need to create a ratio to use it. Cosine law, you need either all the sides, so all sides, or you need 2 sides and an angle, or 2 sides and an angle. So I can technically use cosine law for this one, but what will end up happening is we'll end up finding like what do I have here? There we go. I'll end up finding like one of these opposite angles here, so it's not going to work out so very well. But sine law is going to help us in this one because we can set it up, and maybe sometimes the best way to figure out which of the tools to use is by actually setting up the law. So sine law is sine A, so the angle over the side, over sine B, side B, over sine C, side C. Or you can like invert that and just say A over sine A equals B over sine B is equal to C over sine C. Sorry, I ran out of space there, but both of those laws work. You can flip them back and forth. What's good here is if we go ahead and name this triangle, let's give it some letters. We'll call this will be A. If that's angle A, that means this is side A. We use the opposite here. This is angle B, that would be side B, which would make this angle C, this becomes side C. So with that information, angle A is unknown, and angle inside A is unknown. So they stay the exact same. Sine A divided by side A. We got no info for that one. For B, if we scroll up just a little, we got angle is 102 and the side length is 35. So that works out. We got some info here. So sine 102 over the side length of 35. And for C happened to be our theta. We're actually looking for that. Theta, we'll call it, okay? So we'll say sine theta, because that's actually what we're looking for, divided by, oops, why that happened? Divided by, side was 20 degrees, or sorry, 20 meters, I should say. Okay, so we can use the sine law. I'm going to move it over here because we have what's a complete ratio. This is really important. We both have a side and its opposite angle. And once you do that, this is going to equal something. We can calculate that, and that can help us solve anything else. Now, we're kind of stuck on this part. We need at least one other part, and I don't have either of these, so that's not very helpful. But I do have a measurement here, and it just so happens we're trying to solve theta, so this will be the most efficient one to use. So I can kind of drop off sine A and side A. We don't need those anymore. They're not helpful for our question, so we can rewrite it one more time. Sine 102 divided by 35 is equal to sine theta over 20. Now we want to get sine theta by itself. And because there's a division sign here, what we can do is we can multiply both sides of the equation by 20. Okay? When we do that, this will create a 1, or they usually call it canceling out. But what's important is it'll leave us with sine theta, which is really good. We've isolated a little. I'm not going to calculate it yet. I'm just going to keep it like this, 20 multiplied by sine 102 over 35, okay? And then I still want to get theta by itself. That's the goal here. To move sine to the other side, we use the inverse. So we end up with theta is equal to sine inverse of, and all of this has to be calculated beforehand, but 20 times sine 102 divided by 35. So now what we can do is we can just plug this into a calculator. Now I do want to make one note here. Sine 102. If you remember the cast system, okay, 102 happens to fall in, if this is quadrant 1, this will be quadrant 2. 102 falls in this quadrant here, okay? The question is, what's going to be positive in that quadrant? Will cosine or sine be positive in this quadrant here?
Sine.
Sine, yeah. So we're still going to end up with a positive answer, so that's going to check out for us. Because if we use cosine, we'd end up with a negative answer, and that's going to change some things for us. So we'll have to probably work with the opposite, the acute angle, rather than the obtuse angle. Since we're going to end up with the positive, we're going to end up with the exact same ratio. And we'll plug both in. Just as a side note, because we're going to jump to the calculator in a second, the acute angle that is associated with 102, if we call this the obtuse angle, the acute angle would be 78 degrees, okay? So I'm going to jump to a calculator here. Let's do Desmos scientific calculator. Here we go. So scientific calculator, let's do sine 102 and sine 72. Is that right? Oh no, not 72. 78. There you go. So notice we get the exact same ratio. Okay, when we put those not ratio, sorry. Well, actually, technically it is a ratio. We get the same decimal value. It's harder to understand as a ratio, but we get the same decimal value. So it didn't matter which one we worked with, is which I was talking about before. Now, our actual equation, I'll write it on the side here so we don't quite forget.
Mm-hmm.
I'll have to write with a mouse, which will not be very good, but it's 20 times sine 102 divided by 35. Okay, we wrote it there just so I can type it in the calculator and we have something to reference, okay? So I have 20, I'll put in brackets, sine 102 divided by 35. Okay, so it gives us a ratio, but actually more importantly, I can do this all in one step. If I just do my function, I can do sine inverse of that value and hit enter. And there's our value, 33.98, so approximately 34 degrees. So when we jump back over here and we go down, and we calculate all this, After we've calculated it, we'll find out this is approximately 34 degrees. So if we zoom out a bit and jump back up, that means the angle that we started with way up here, okay, this angle is actually approximately, I'll do it in green, 34 degrees with the ground in this case, okay? So it's a pretty big question. There's quite a bit we had to do in it. We went slowly and broke up each part, but there's quite a bit to a question like this. We had to draw out that image. And once we get the image, we decide what that internal angle was. We had to do a little inferencing because we knew the vertical was 90 degrees. Then we had to choose which tool to use, primary trig ratio, sine law, cosine law. And once we did that, we had to evaluate and isolate for theta to solve this question, okay? So a bit in that question, there's actually quite a bit for it to
I
do.
do it differently.
Ah, okay, let's take a